In this quick video, I'm going to go over some of the physics behind the aurora, or the northern lights. To do that, I have an old school TV. This TV is a cathode ray tube, or the old heavy tube TV. If you've ever tried to move one of these, you'll notice that they're really quite heavy. Why are they so heavy? Well, it's this large glass tube. Now, it's a large, very heavy glass tube. Why does it need to be so heavy and strong? Well, inside of this glass container is next to nothing. It's a near perfect vacuum. Just to show you, I have a sample of glass from another TV, and you can see it's nearly a centimeter thick. This very heavy glass is what's required to support the almost nothing on the inside of the container. Now, how does it work? In the back of the TV are electron guns. The electron guns fire a stream of charged particles at chemicals on the front side of the screen. Now, you can see in this piece of glass here, there's a little bit of the residue from some of the chemicals from this old TV. Now, some of these chemicals, when struck by the charged particles, will glow red, some will glow green, and some will glow blue. Currently, the electronics on this TV are telling the electron stream just to hit the blue phosphors, or the chemicals that will glow blue. How do they do that? Well, electromagnets will direct the stream of charged particles. So again, the electronics in the TV right now are directing the stream of charged particles just to hit the blue glowing phosphors on the screen of the TV. Like I said, they're directed by magnets. And so here I've got an independent bar magnet. Now watch what happens when I hold the bar magnet near the TV screen. You can see I can direct the stream of charged particles, and now instead of having the charged particles hit the blue phosphors at the top end of this magnet, the charged particles are hitting the green phosphors, and at the bottom end of the magnet, the charged particles are hitting the red phosphors. And so using magnetism, we can direct the stream of charged particles, because charged particles are indeed, their path is affected by magnetic fields. Now I have a super strong neodymium magnet here, and just when I even hold it somewhat close to the TV, I can dramatically alter the colors on the screen. This is quite dramatic also if I have a picture, because the grass, which is normally green, may appear a different color, or the sky, which might be towards the top of the picture, which would typically blue, could also be altered in its color if it's in the presence of a very strong magnet. So how does this relate to the aurora? Well, in a very similar way, there is a stream of charged particles constantly emanating from the sun. We refer to that as the solar wind. The solar wind is this outer atmosphere of the sun, and it's constantly streaming through space at something on the order of 1,000,000 miles an hour. Sometimes it's a little less. Well, as the stream of charged particles flying through space come near the Earth, they interact with the Earth's magnetic field. Of course, the Earth's magnetic field is strongest near the North and the South Pole. As the stream of charged particles interacts with the Earth's magnetic field, it directs some of those charged particles down in the stronger zones of the magnetic field of the Earth, and those charged particles interact with chemicals in the Earth's atmosphere, causing those chemicals to glow in some of the characteristic green and red colors that are known for the aurora. So, very similar to the TV, where we have charged particles coming from electron guns in this case, hitting glowing chemicals on the TV screen, but being directed by magnetic fields. With the case of the Sun-Earth system, there's charged particles coming off of the sun, flying through space, interacting with the Earth's magnetic field, which directs the charged particles to interact with the atmosphere near the polar regions of the Earth, causing those areas to glow.